introduce Ricardo Alarcón, who will give the third talk today. For those who don't know Ricardo, who is an assiduous participant in this symposia since their creation, the research interest of Professor Ricardo Alarcón are the design, construction, and execution of experiments in basic nuclear science. Presently, his experiments address fundamental issues in nuclear physics, such as precision measurements of the neutron decay, with the aim of improving the precision of the associated quantities and to test the standard model. But Ricardo today is surprising us with a talk related with protons beams used in radiotherapy. Ricardo. I can give you mine. I don't know if there is a portable mic.
Can I use this one?
Yeah.
Yeah.
You prefer it?
No, it's mine.
I don't know. Could you turn it on?
Perfect.
I will tell you after 30 minutes that
Perfect.
you have 10 minutes left.
Yes.
Okay.
So this is the one, the top one, and the top one is the lesson, and this is the yeah. Right? Can you give me this? Okay, good morning. It's a really great pleasure to be here back at UNAM and back at the symposium. And as Maria Esther just said, I'm going to talk about something that it's fairly new that I've been involved lately, and that it has to do with physics that is very well known, which is the physics of multiple Coulomb scattering. That physics has a relevance for therapy, because when you treat people with protons, especially if they are gonna go through the patient and you wanna take a radiography or you wanna do a scan, then the process by which the proton interact with the matter is through this small Coulomb interaction. So a precise characterization of that process is actually what helps you in moving forward. This is a collaboration between a small company that is Proton Calibration Technology, my group at ASU, and the Mayo Clinic in Arizona. We would not have been able to do this if we would not have access to the clinic, to their beams. So what you see here in that picture, that is a 40 millimeter by 40 millimeter scintillator through which a therapeutic beam of about 4 to 5 millimeters in diameter goes through. And as you know, as soon as the high energy proton will go through a very thin scintillator, the first thing that you see is luminescence. It's isotropic. And behind that scintillator, there is a mirror. It's called a pellicle mirror, a pellicula. It's a very thin mirror. They are used in basic science all the time. And a digital camera that is focusing on that mirror in the opposite direction in which the proton go is what you see. That's the viewfinder that you see in the digital camera. Okay, so I need to move forward now, and the advance is this one, isn't it? This is the laser. And I apologize for that. Should I do it manually? No? Yeah. This one. It is that one. Perfect. So this is a brief outline. So I have to do a brief introduction to proton therapy, proton radiology, and proton CT. But it's going to be a biased introduction because I'm not an expert on it. But I will try to, for the sake of the students and those who have not heard about this, to give you a flavor of it. And I usually, when I do that, I like to do it historically. So I go to very back in time when people really started the field, and then I jump into where we are today because I don't have time to go through the trajectory. And then I'll introduce this technique that I briefly described to you. And then the results and that we obtained at the Mayo Clinic, Arizona, and the simulations that we did to understand the results. And then, of course, I will summarize. So everything started in 1946 by Robert Wilson. Robert Wilson is a towering figure in physics, an accelerator of physics. Among many things, he became the first director of Fermilab and actually the architect of that building. So you get an opportunity to go there, you will see that it's a very interesting building. In 1946, he published this paper. The title is Radiological Use of Fast Protons. And it's a very short paper. There are only two figures. The first figure tells you something that now is extremely well known, and people use it as the way that you have to do therapy with proton, is the fact that the ionization curve, this one, as soon as it's getting close to the final ratio, the proton explodes. And this is the famous Bragg peak, in which he pointed out that the Bragg peak for a beam is the same thing for a single particle. And then he proposed that actually you can use varying energies and create a flat distribution here that I will show you later. Since then, Harvard didn't pick up on the idea right away. It was actually Livermore, Lawrence, no, not Livermore, Berkeley, Lawrence Berkeley. And Lawrence have just built the first high energy cyclotron there, the 340 MeV cyclotron that he patented. And throughout the 50s, they carry out research with people also, in addition to basic research. And so I just highlight here a paper that they really treated people, and they were the first on record to do that. Then in Europe, in the mid-50s, in Uppsala, with 155 MeV cyclotron, they saw the first patient in 1957, and were the first one to use the idea of the spread out Bragg peak that we will see later on a little bit. And so then Harvard had a cyclotron in the late 50s, 160 MeV cyclotron, and they did very important studies regarding the biological effectiveness of protons. And then they partnered with the Massachusetts General Hospital, who were the first ones to do that. And by the time they stopped doing the facility, they have treated over 9,000 patients. So the picture today of proton therapy, it's amazing. It's all over the world. All over the world there are facilities. There are, this is a map that I take from this group, which is the Particle Theory Cooperative Group. And this picture is about, I think, 10 years ago, because here in Latin America, since then, in the last few years, there has been 6 centers open. Sao Paulo, Mexico City, Buenos Aires. Buenos Aires will hold the 63 annual particle therapy conference. They just met in Singapore. It's a year conference. If you are in particle therapy, that's the conference that you go. And there is one in Medellin, another in Santiago, Chile, and one just recently opened in Lima. Now, if you are around the proton therapy field, you are going to hear about the range and certainty in proton therapy. And what it is the fact that it's actually quite difficult to predict exactly where the proton is going to land and deposit most of its energy. It's a problem that is easy to calculate, but in practice it's not easy to accomplish. So the therapy is a very successful therapy, but it has its critics. And it has to do with the fact that, you know, when you debate therapy, you have to say, well, which one is more effective in terms of how patients have recuperated and things like that. So the contributing factors to this uncertainty, the contributing factor to this uncertainty, some of them are patient specifics, and then we cannot do anything about it. In the sense that people move or they're anatomically very different from one another, so that's difficult. The other one, and this is the key, it has to do with the fact that when you are going to do proton therapy and they want to know what is going on, what is going on in the region that you are going to be treated, they are going to do an X-ray CT. They are going to do an X-ray CT has advanced to an extraordinary level these days. The problem with for proton therapy is that when you use X-ray, you have to convert the tissue density that you get from X-ray into a stopping power for protons. And we will talk all about stopping power for protons today. Now, of course, there are mitigation strategies. One of them is a very robust treatment planning, and today is state of the art in terms of simulations and things that people do. The other mitigation strategy that is connected with this, the one that I'm going to be talking about, is that whether you can have advanced imaging techniques other than X-ray. Can you have proton CT? That's the question. And there are other things. There is in vivo range verification, for example. I've been involved on that. These people actively work on it, but it has not moved into the clinic. It's still in the laboratory. And beam modulation, advanced delivery techniques, that has to do with scanning pulses, and it's a very advanced technology that came up along when the synchrotron came into play after the cyclotron. So I have to remember, this is the one, yes. So let's talk about radiography with protons and proton CT. So the seminal paper is in 1963 by Cormack. So he solved the problem of finding a real function, knowing a straight trajectory of particles that have gone through. And he applied that to 3 problems. And the third problem he applied to is the one that we are interested in. It's in the determination of a variable density of matter with constant chemical composition using the energy loss of charged particles in the matter. That's the key. Then the same Cormack with Kohler, they actually did a preliminary experiment. And they found very interesting things about the property of protons compared with X-rays. Because the way proton probes the matter, it probes through these very small interactions, whereas the X-ray is broader. The X-ray is through absorption. And so today, there are efforts on proton CT and proton radiology all over the place. And so this table lists most of the efforts that we know of a few years. So PRAD is proton radiography, PCT is tomography. And you can see is that it's all about particle detector technology. It's all about silicon strips, gems for the tracking technology, and the rates in which this detector needs to operate are not trivial. And these rates are actually an underestimation of what you will actually need to do if you are going to be in real time observing this proton. We are talking about tens of megahertz to hundreds of megahertz. And everybody who has experience with those detector systems know that it's not easy to operate. So I leave this plot here because I want to discuss it with you because this is an example of how this detector system looks like. So they look like the following. So you have a beam of protons. They could be coming out of a nozzle or wherever they are coming from. So in order to reconstruct the trajectory of those protons as they go through a phantom of a patient, you need to have tracking planes before, tracking planes after, and some kind of energy detector that is going to give you the information about the proton energy. A couple of things here. Every time that you have tracking planes and detectors like this, you are going to introduce multiple Coulomb scattering on the proton that you are going to have to take into account if you want to reconstruct their trajectory. Second, perhaps the reason why these tracking planes are here and here is because of the rates. Because the rates are so high that if you don't have the front tracking plane, suppose you say, why do I need to find the direction of the proton if the accelerator is telling me that that's what it is? It's very difficult to do better than the accelerator to where the protons are at a particular point. But the reason is probably background. So with that, let me give you final thoughts on proton radiography and computed tomography. So another important point too, this is relevant in the sense that the range uncertainty problem is not the only motivation for proton radiology and CT. Early on, it was realized that proton radiography provides a better density resolution and tissue control compared to conventional X-ray imaging. So you can use proton radiography to verify the patient setup. It has the advantage, one of the problems of X-rays are metals. So you have an implant or you have anything like that, you are going to have that the CT scan is going to have problems on that. But most important for this talk is these last 2 points. The point is that the ultimate proton CT system, it will have to be mounted on a gantry, and I will tell you what the gantry is. Because a gantry is a device that rotates the beam 180 degrees, and the patient is just sitting there. So you can shoot the patient from different directions, which is what you need for therapy. The problem, though, is that to get there is probably unlikely at this point, because you will have to make a major redesign of proton therapy facility to accommodate this detector system that I just talked to you about. And we will see a picture of that probably will help in understanding that particular point. Yes. Yes, a typical proton energy we'll get into a second, but okay, it's a good point. To do radiography and proton CT, you need a proton energy that will go through. So that has to be, the minimum is about 220 MeV, which is about what the facilities have now. But if you have 500 MeV, it's pretty good too. So what we are studying right now is that we think that if you capture a fraction of the isotropic luminescence that is emitting when protons go through a thin scintillator using a digital camera. So if I put a piece of material in front of this scintillator, then I'm going to be able to see what is the profile of the outgoing protons with this technique. And it will become clear as I go on. So the physics is simple. It's the physics of a stopping power. It's well known. You can go to a site that is run by NIST. You can put the material and it will tell you the stopping power of protons as a function of energy. Now, if you're in a scintillator, the scintillation emitted by unit length is given by the Birk's equation, okay? When there is a very high energy charged particle going through the scintillator, and the scintillator is very thin, this term here doesn't contribute as much. So what you have, that scintillation that you see, is proportional to the energy lost in the scintillator. No big deal. And so this is the way we reason. We reason that the scintillator can give you about 40,000 photons per MeV. So a typical proton energy of 200 MeV is going to lose 1 MeV. So you're going to get 40,000 photons out of that. Now, if you capture only a fraction of that, then this fraction is about 1 part in 1,000. That it has to do with the fraction that the mirror is from 4 pi, and the reflectivity of the mirror, which is 50%. The number is not important because you are not going to need it to do. You don't do absolute measurements. But they are sending you more than 10 to the 8 protons per second. So even though this will give you a few photons per proton, per frame, a frame that we typically use is 100 milliseconds, then you are going to get about the same number of photons, the number of protons, 10 to the 9, huge rates. So we proposed the following measurement. We said that we wanted to position the scintillator and have the beam energy to come here in steps between 80 and 220 MeV. And we did that in a step of 20 MeV. So we reason that the yield that we will see, the area of the distribution or the volume of the distribution, it will have to be directly proportional to the energy loss. So if I then position an object in front of the beam, then the protons are going to go through, but they're going to have a different energy after they leave. And then I'm going to measure now a different sum. The proportionality is going to stay the same. And if I think that everything works well, and never does, then if I take this ratio, I'm going to be able to tell you what was the final proton energy, because I get the energy loss in the scintillator, I come here and I tell you the energy of the proton. I go here and I tell you the energy of the proton. And in principle, I should know the energy that it was left out in the phantom. The idea, of course, is that you will then take these measurements and you will rotate this in different directions and so forth. But more important, we realize that what we were really probably looking at is the multiple Coulomb scattering from protons, in the sense that you are going to see the beam first. When you put this, then you are going to see again a distribution, And the standard deviation of that distribution is going to be given for a single proton by the well-known formula in Molière that you can find in the particle data group. That's the idea. So let me tell you a little bit about the facility, the way we do it, very briefly. These are state-of-the-art facilities. These facilities cost over $300 million when they built it. And Mayo Clinic Arizona was very happy that a donor gave them this money. Because Mayo Clinic was building it out of their own money, one in their Rochester headquarters. Okay, so this is a synchrotron that is fed by a linear accelerator, and the beam can be sent to 5 different places. And these 4 big places, these are treatment rooms. This is where patients go and get treated. Very wisely, they leave one research area for a fixed beam in which people can do calibrations, research, whatever they want to do. So that's where we went. And this is the treatment room. So these treatment rooms are huge. The beam comes in this direction and goes through this gantry. And then it's come out and it hits the patient. This gantry can rotate around. And anything that you build to analyze what happened after the patient, it will have to be locked with this gantry. And that's why this very complicated detector system, you will have to redesign this to accommodate those detector systems working that way. To accommodate a thin scintillator, a camera, and a mirror is a very different problem. So this is their nasal design, and this is just to tell you that they can scan the beam horizontally and vertically, and so they can, do this, what is called the spread out Bragg peak that we mentioned at the beginning. What you do, you pick one energy, you get one peak, one Bragg peak. You lower the energy, you get another one, and you monitor the intensity such as the sun is a flat out radiation over a particular area. This is our setup. We were there March 22nd, less than 3 months ago. And the beam comes in this direction in the fixed research area. We put our scintillator there. This is the pellicle mirror, and this is the digital camera. When we put phantoms, then we arrange them in front of the scintillator. A key aspect of what we're doing is the fact that this digital camera is looking away from where the proton is going. So not the only thing that it sees, but it really sees the light being reflected there. So this is what we did. This was our logbook, 1 page, 3 hours, 5 p.m. to 8 p.m. We brought a camera, we brought the scintillator, the pellicle mirror, and phantoms. The camera was always set in terms of focal length and shutter speed at the same values. And we measured with no phantom the energy response between 80 and 220 MeV in 8 different settings. And then we picked the highest energy and we put 3 acrylic phantoms, first 5, 10, and 15 centimeters long. And also at the end, using 200 MeV, we look at 2 biological phantoms that were provided to us by the Mayo Clinic. One is muscle and the other is bone. So this is the online data now. This is when it gets interesting. Oh, yeah, you're trained. Oh, boy. So the data, it comes in this way. Any of these points is shot by the camera, and it's the sum in the sensor. And so there are about 40 shots here, and we shot about 3 shots per second. So 20 seconds of data, that's it. And these correspond to seconds when there is no beam, because it's a separation between the pulse beam. So let me just hurry up a little bit here, because, so this is a typical beam, by the way. And this is a pulse, and it actually has a lot of mini pulses. So a lot of the fluctuations that you see here are due to the fact that there's no synchronization yet between the camera shutter and the delivery of the beam spots. You need to do a data reduction. You do apply a medium filter, which is a standard thing in digital cameras. And after you apply the filter, which is described here, you get a very nice Gaussian peak. And this is the edge of the scintillator. To do the data analysis, the students did it. They got Python packages. They defined the brightness as a volume of Gaussians, and these are independent Gaussians, so you can separate them. And this is the response of the camera, the center of the sensor for 100 MeV beam, and this is 220 MeV beam, and they are perfect Gaussians, and they are broader, a lower energy than a high energy, totally in agreement with what Hitachi is the accelerator was built by Hitachi that they prescribe. So we measure the yield for all the energy range, and the red curve corresponds to the NIST data for a point proton. The blue, of course, is the experimental point. Between 100 MeV and 25, actually, the agreement is much better, which is the region of interest. And if you look at the variance of these Gaussians actually is very tight. And so it works reasonably well at that level. Then we put the phantoms. So this is the acrylic phantom at 5 centimeters, 10, this will get a wider, 15 gets a little wider. So first thing that we did, we took our calculator and we calculated the Molière formula. Then we took one of these Gaussian, the XY Gaussian, and we did the ratio, and we got a constant number. So we are seeing multiple Coulomb scattering and nothing else. This needed to be corroborated with the J-Amford simulation, which is the standard to do this type of interaction. It's an easy problem for J-Am. What you see here is a point beam going through the acrylic. This is the acrylic. So and then the proton, of course, start going multiple scattering. And when we ask the code, what is the proton distribution right outside the phantom? And then we put a 1 centimeter scintillator here, 1 millimeter, exactly the one we have, and we ask for the energy loss. And of course, we also send a Gaussian beam. And the Gaussian beam that we send is this histogram, when it's measured here, and this is the fitting of that histogram and the fitting of the beam that we measured before in the previous picture. So it looks pretty good. So look at the 5 centimeters. This is the data, and this is the J-Amford simulation. The Gaussian of this is on top of this, and the energy loss now in the scintillator is given by, we don't measure this, of course. This you can ask Jan, well, what was the energy deposit in the scintillator? And this is the Landau function of a high energy particle going through a thin piece of material. And it was 1.15 MeV. So you go back to this curve and you say, well, it was 1.15 MeV. So that proton energy was about, the mean of that proton energy is about 195 or so. So you lost 25 MeV in the material. More interesting, actually, is This is the thing with Gian, you can ask questions. So this is the proton beam, the point beam. The first thing that you see here is the single proton spread out only a fraction of a millimeter going to 5 centimeters of acrylic. It will spread out a little bit more, but in the end, the trajectories are almost straight. This is what happened to the Gaussian beam. And the Gaussian beam, it has the same thing. They all, no matter in which beam you are in this distribution, the energy loss is always the 1.15 MeV plus minus 0.19, and the tails are over there, the tails of the distribution that I showed you before. So the Gian simulations tell us that it doesn't matter if you use a point beam or a Gaussian beam, the energy loss in this scintillator is going to be the same. It indicates that the proton trajectory are very close to a straight line, which is actually quite suitable for tomography. This was bone and muscle. Bone is denser than muscle. Looking at this Gaussian, it's hard to tell, but you just look at the standard deviation and you can clearly distinguish between these densities without any problem. So, summary and outlook. So, we are developing this new technique because we want to characterize the multiple photon scattering of therapeutic protons right outside a phantom of a patient. We think that that's the key. And this technique gives you just that distribution. It doesn't interfere, nothing interferes with it. And we give you this result, and we think that this configuration actually will allow the gantry to rotate and be attached to a gantry. To move forward, I think we are, of course, seeking funding. There is a small business grant that is pending with the National Institute of Health, and the company is always looking for private funding. I think if we are hoping to hear that very soon, and we certainly have the scientific manpower to move forward. We need to optimize the technique, of course. We need to do this synchronization that I told you about. We need to use less beam, actually, than the one they gave us. We need to revisit the camera options because we don't need 24 million pixels to do this, which is what this camera. And we need to optimize the geometrical configuration. So we will run a program in this research area that we hope will lead to the first images. So a special thanks to the team. This is the team in proton calibration technology. Paul Malkin is the CEO. This is the gentleman that worry about the business part. Very thankful to two dear colleagues at the Mayo Clinic. Martin Bues, who is a physics PhD, and Dr. Robertson too, and both, especially Daniel, spent all the time with us handling the beam. And to my group. So my group is Skylar Clymer. He's a grad student who is also working on an experiment that you are going to hear from Dinko in a couple of days. But in his spare time, he does this Python thing and he loves to do. And Lucas Domer, he's an undergrad. He will be a senior next year, so will be this undergrad. And he, with this high school student who will be entering ASU this fall, so we might have him for 4 years, they made a Gian simulation. And he did the plot of the intensity versus beam energy, and that's all I have to tell you. Thank you so much.
Thanks very much, Ricardo. I have a question. So the idea is to modify at the end, is to modify the facility so as each patient before being treated gets a radiograph with a beam that is higher in energy, because these energies are to deliver the Bragg peak at the tumor, not
Yes.
to traverse the patient. So you will have to increase the energy of
Well,
the
no,
proton
at 220 MeV, you transverse the
beam. You
patient.
transverse.
Yes, and so the idea is to try to have a proton CT system. Now, how you're going to use it, whether you can use it while you are treating the patient, you can certainly do it to do the treatment plan. You can take the system and have the patient carry a CT with this technique. Now, the main point for us is that we think that this scintillator and a mirror and a camera is something that you can engineer to already attach to these gantries. That should not be a problem that an engineer will work.
Hi, Ricardo. So maybe I missed that. Maybe you said that, but let me repeat again. I had the impression that the data show like a little halos or additional tails
Yes.
that are not. Could you explain that? Or
Yes, I think that's because the camera is too sensitive. We think that when we just we were even in the room was not dark enough. Okay, so we will take pictures and we will see all of these things in this flat part that you're mentioning.
But I got the impression that it increases.
This flat part that you're mentioning.
But I got the impression that it increases. It's not flat as a function. I mean, when it changes with the different thicknesses. So it's not like it's actually.
It's probably, yeah.
Talk, and I invite the fourth speaker in our morning session. I will introduce Professor Pawel Moskal, a professor and the head of the Department of Experimental Particle Physics and Applications of the Jagiellonian University in Cracow, Poland. He has received a long list of awards related to innovation, in particular, inventions related to medical applications of physics. He is the inventor of a cost-effective positron emission tomography system based on plastic scintillators and positronium imaging. He will present this first positronium imaging of humans using a modular, demodular JPET scanner. Pawel, welcome to Mexico.
Thank you very much for such an introduction. I would like to present you the first positronium images, and I will explain what we mean by the positronium imaging. This is a medical diagnostic technique which we are pioneering in Cracow, and we are developing a scanner which we call JPET, and this is the abbreviation from our university. I will first tell a few words about the university. So I'm coming here from Poland. These are a few photos for those of you who never been to Cracow. Maybe you can consider someday for the revisiting. And since our rector is sponsoring me for that travel, I will tell a few words about the university. So that JPET is the name we chosen for our group. The longest Jagiellonian positron emission tomography. This is the name of the King's family who founded the university at this time. And this is so far our best student. I think I do not need to tell who is that. He was studying astronomy at our university. And now this is our group at the Faculty of Astronomy and Physics. So it's we try to continue as much as we can. The group is nuclear physicists who were seen here, and the medical physicist. At the screen here I can see so we are trying to develop a technique which are some of them are quite well known in the nuclear physics. So what we are trying to do is to apply the nuclear physics technologies to medicine, but also to the studies of the fundamental phenomena like discrete symmetries in the particle or particle and nuclear physics. And these are the things I would like to talk today. But if I will have time, I will also show you how we are monitoring the beam. So at the previous talk, we have heard about the proton beam therapy, and with that device which we are developing, one can also make an online beam verification. So this is our group now, CINEBL. We are nuclear and particle physicists, and the medical and biophysicists. We joined the effort of Professor Stępień, who will talk on today at another invited session about the biomedical aspect of that research, which I will present you to today. This is a photo of our group from this year. So we are very proud to be not only interdisciplinary group, but also international. By now we have colleagues and postdocs and PhD students from more than 10 In case I will not manage to the end, I will show you our result at the beginning. So this is a tomography system which we developed, 50 kilograms, which we used for the first imaging with that modular and portable PET from plastic scintillators. These are the first images, so you can recognize the organs here. These are the density distribution of pharmaceutical in the organs. This is Siemens, and this is our images in not optimized conditions. And this is the photo of the first patients for which we did a positronium image. And by positronium image, we understand the image of properties of positronium atoms inside the humans. In that case, it was inside the brain. So I will not go through the whole protocol, but just will tell you that that patient has a glioblastoma tumor. And this tumor was cured with actinium emitting alpha particles. So that actinium was attached to the substance which is having a high affinity to the glioblastoma tumor. So that substance, this is the molecule, was attaching to the tumors, and actinium was attached to that emitting alpha particles. And what is very nice, this is an experimental study, that patient was living already 11 years after the recognition due to that therapy, or thanks to that therapy. And typically the patients with glioblastoma are living about 1 year only. But we were, for our studies, development of this positron emission tomography and that positronium imaging, we were taking advantage of the fact, and here you see this is all in nuclear physics, that the gallium isotope, gallium is beta plus emitter, was also attached, and the doctors administered that gallium also to see where that pharmaceutical is really attaching or distributing, just to be sure that the right places are cured in the brain. And the gallium is emitting positrons, as you see here, but the daughter nucleus is excited, at least in some percentage. So it's emitting positrons, turning to the thin in an excited state, and this thin is de-exciting by emission of the, which is called prompt photon, the excitation photon of about 1 MeV energy. And this is why we did that trials with that gallium, because that photon, that nuclear de-excitation takes on the average like 2 picoseconds. So we may say it's immediate. So when measuring that photon and the time when it was registered or emitted, we know when positron was emitted into the body. And from that, we may study the mechanism or what was really going before electron and positron annihilated. So by measuring that photon, which is shown also here, and by measuring the photons from electron-positron annihilation inside the body, we may determine the time, how long it takes for each event to annihilate. And in a body, which is not used by now, the electron and positron annihilate not only directly, like you can see here, but it may form also a positronium atom. And here are a few examples of positronium atom. It's an atom of electron and positron. This atom lives in vacuum about 100 nanosecond when it is in the spin 1 state, and 100 picosecond when it is in spin 0 state, but it may undergo various processes, which I will discuss later. And from that time, we can infer about the intramolecular structure, because the lifetime depends on that structure. And this is what we know from physics. But now, what medical implications it has is a matter of studies which we are just now, we may say, pioneering. And this is a standard image of that patient. So you see here density of annihilations, and one can recognize that glioblastoma cancer. And this is an image which shows the distribution of events when we suspected a positronium atom, which are those when we registered in addition that photon. The statistic is very low because if you look for that branch of decay, when the gallium is emitting positron and then going into excited state, is only 1%. So we could use only 1% of the events, and then in addition to register gamma is another decrease of events because of the efficiency. But anyhow, we were able to calculate the lifetime of, the mean lifetime of orthopositronium atoms for the glioblastoma cancer, for the salivary glands, and for the healthy brain. We divided the person into 3 regions. And what you see here, and this is what is exciting for us and indicating that it may be useful for the medical diagnosis, are the differences shown here in color. So in the cancer, the lifetime of positronium is lower than in the healthy brain, and in the salivary glands, it's something like in the middle. So now I will, this was the main result I wanted to show you, that we developed the system, very low-cost system when one can make an images, and light and portable, and that we managed to make this first positronium images. This is the scheme of my talk. I will explain one more about the development of the Jagiellonian positron emission tomography. Then we'll explain in more detail how we get that images. And I will also present you what we are doing in the fundamental physics studies, and maybe also about the proton beam monitoring, if there will be a time. So we are mainly aiming at introducing plastic scintillators, and the aim is to make positron emission tomography low cost. I was taught not to use the word cheap, but we like to make it cheap. And the other reason is so to make it for the broad community in the world. This is we are developing that method to make it more specific. So to know more in vivo about the example, the grade of the malignancy of tumors. And if you look at that map, you may see that why it's important to develop some diagnostic methods which is cost-effective. And we are physicists, we often use the word in the first order. So if you look at that map, you may say that in the first order, nobody in the world has access to the positron emission tomography. So there is less than 1% of clinics having that systems. This is zero, so some countries has nothing, many of the countries. Most have between 0 and 1, so if you look here in Latin American countries, it's between 0 and 1, maybe somewhere in the middle. I'm from Poland, we have close to 1, or almost 1 per million citizens, so also in that range. And there is only few countries like US, Italy, who has that in the range of 10 per million citizens. And it is still not enough to make any screening. So to deliver the word technology which would lead to the stage when it is in the US, one need to make it less expensive. And I will show you later what are the main costs of that. This is how we progressed. So it's not like few months it's almost more than 15 years by now development, coming from the patents applications, going through the various stages. I will tell you about the results from that tomography system, that one which is portable, and I will show you what we are going to build by 2028. This is a figure showing a standard positron emission tomography. So the patient is administered the molecules with beta plus isotope. Typically it is fluorodeoxyglucose. It's distributed in the body, metabolized. And what we are measuring annihilations of beta plus in a body via detection of the photons. And this is correlated with that isotope, which is correlated with the molecule to which it is attached, which is correlated with the metabolism or with the density of receptors, depending what is measured. So the main problem to distribute it all over the world now is the cost. So the crystal detectors are used for detecting the photons, and that crystals typically now it's LISO, which cost is like about 1/5 of the price of the gold. So if you have a tomography system with 20 centimeters, this is like a ring of the gold with 5 centimeters. And this is half of the cost. Another half is electronics. And therefore it is very expensive. Typically nowadays, although the prices is going down, but typically it's about $2 to $3 million for about 20 centimeter. Nowadays they are appearing or emerging systems with 1 meter, which costs $9 million, 9 million. There is one in US who Chinese built in Davis, which the grant was for $16 million, and who knows how much Chinese company added to that. So probably about 20 millions the cost for 2 meter. So these are very expensive devices. And now our main change which we propose is to change crystals to plastics, which sounds easy, but it is not that easy in practice, because plastics have no photoelectric effect for photons in the range of 1 MeV. They are from hydrogen and carbon. So there is low Z, there is no photoelectric effect, and only Compton effect. And the main interactions used in the tomography now is the photoelectric effect. But with the plastic, we may make the long bars or long strips, read out them at the edges, and calculate the position of the interactions, not from the place of the crystals, but from the time difference of arrival of the scintillation photon to one side and to the other side. This was the main idea. This is the comparison between crystals and this plastic scintillator. This is an old table. I still used here polymer because when writing a grants, these were always rejected, claiming that with plastics you should not make a PET. It's not, it makes no sense. So I was trying to be clever and call it polymer in the grants. It also did not help for a long time. But the main feature here is that they are like 7 times less dense. So roughly 7 times less electrons in the cubic centimeter means 7 times roughly less probability for the interaction. But we need to interact at least 2, so it comes to almost 49. It's not, it's a rough estimation. But the advantage is that the timing, the photons are emitted in the much shorter time, and they are not absorbed in the scintillators. One can use even 4-meter scintillator and still have a light at the end. In case of crystals, few centimeters is already blocking the full light. So this may be also used as a light guide at the same time as a detector. The efficiency with that configuration, we compensate by making few layers. So this is how we compensate for the efficiency. And the cost effectiveness is not only scintillators. So the plastic scintillators are about 50 to 80 times cheaper than crystals. Whatever you take, BGO is 2 times less costly than LISO, but roughly it's about 50 times cheaper than crystals. But additionally, the electronics, all the photomultipliers and the electronics is proportional here to the cross-section of the detector, not to the area of the detector, like in the standard PET tomography system. So altogether, these 2 aspects are making the system, depending how one make it, but between 5 to 10 times. 5 to 10 times, not 50%, but order of magnitude less. To develop that, we need to develop a lot of technology to deal with the very low signals. We sampled them, but I will not go through that details today. We have published a lot of publications on how it is done, and also altogether by now it's like 40 patents for all those technology development. And I will show you some results, how it works, starting from that prototype. So here you see those scintillators. This is sparse with holes, not because there is any great idea behind, but because of the generosity of our ministry. But anyhow, we show that this tomography system works. This is how it is to scale. We have 3 layers of scintillators. And another difference with that tomography system to the standard one is that we have no restrictions to how many photons are registered. So we can look for the annihilations with 2 photons, 3 photons. If there is a prompt, 4 photon, we have a triggerless. So continuous detection, continuous mode for the detection, for the data acquisition. For that physics experiments and the first studies, we use aerogels or polymers to produce positronium. So here is a sodium source that dot there with Kapton foils covered with positronium. And here you see how we register that. This was the first anthropomorphic phantom, a human being like a cylinder with the stomach. And we used that to show that we can reconstruct an image. So the annihilations were at the surface of that cylinder. And this was our first image. It's not really even the image, it's just the calculations from time differences, the position of annihilation. So this is a scatter plot of the annihilation positions. This is an image. But with that detector, we have also shown that one can do images into annihilations into 3 photons. And this was something new. The prompt gamma, that one for starting, we can distinguish from the annihilation photons just by energy loss measurement. Here is a typical spectrum. We do not have a photoelectric effect. So now the spectrum from sodium, for example, is the spectrum from Compton spectrum from this higher energetic prompt photon, Compton spectrum from 511 keV photons, and here the lower energetic photons from the scattering and from free gamma annihilations. This is to show that we could measure the lifetime spectra for those materials in which positrons annihilate. So accidental coincidences, parapositronium and orthopositronium. And then going towards medicine, our first step was to show that we can make this positronium images ex vivo, which means out of the organism. We took the cancer tissues operated from the patients. These tissues are here with the sodium source inside, and the healthy tissues. We put them into the detector and produce a standard image but measuring that additional photon, we could for each voxel here or pixel on the two-dimensional plot, make a lifetime spectrum. And from that lifetime, for each voxel here, determine the contribution from parapositronium, orthopositronium, and all the other components. And this is the image of the orthopositronium lifetime. So this was to show that one can do simultaneously PET and positronium lifetime imaging. But it was also interesting from the medical point of view that we got differences for the cancer tissues. This was cardiac myxoma. It was about 1.9 nanosecond, and this was adipose tissues about 3 nanoseconds. So this was like showing that there are differences in the body between healthy and, if you remember, also for the cancer in the brain, the lifetime was lower than for the healthy brain. This was under the guidance of Professor Stempin, who explained the biological mechanism of that. But I would like to show you that we measured many patients, and for all of them, the lifetime for adipose was much higher than the lifetimes of the cardiac myxoma. But then with that detector, we can now go to the hospital. So we developed such a one, modular, from plastic scintillator, electronics here, around. This was 50 kilogram detector, 50 to 60 kilogram detector, capable of measuring all these kinds of events. This is a photo from the first setup with the colleagues who developed a lot of various methods that it can work. And then we students make photo stations. Then we went to the hospital. So this is the transportation to the tomography system to the hospital. Just 50 kilograms rolled on the, then we installed that. The installation is very short on this is Siemens tomography system, the bed, and then this was an image you already have seen. The bioethical committee gave us 10 minutes, so this was not a very effective or efficient measurement. 10 minutes to come, to set up the detector, to take data, and to go out so the patient can go. The patient had to agree, of course. So this was the action which we were, so even nobody make a film. We were so excited. These are a few photos and this animation made out of that. That I already explained. Now we are continuing the measurements in the hospital with the detector. So you may see some photos from the patients. And again, these are the pictures from General Electric. These are ours, but not corrected for any of the scatter corrections, scattering in the body, accidental coincidences. So there is still many things to improve. Now I will show you more details about that positronium imaging technique, or what we can learn from positronium. So if some of you may wonder how the positronium may be produced at all in a body. So this is a pictorial example. If the positron is entering, this is a hemoglobin molecule. As an example, it's ionizing the atoms and molecules. And at the end of this ionization track, these ionizations are very dense. And at the very end, there is a lot of free electrons which may be bound to that positron. So that this is positron, which is ionizing. At the end, there is a lot of electrons, and positron and electron may form a positronium atom, but it would not live there in such an environment. So it can live in a body only if there are some free spaces between the atoms in the molecules. But the molecules in our body are huge, hundreds or even thousands of atoms, so there are free spaces. And what we are measuring is the properties of that atom within the free spaces between the atoms in the molecule. All this process take about 5 picoseconds. 5 picoseconds. So in the first order, it is negligible. That atoms may be, depending on the spin, it may be long-lived or short-lived. The long-lived is because of the symmetry. So I maybe will not go to the details. I don't know how much time do I have to. Okay, very nice. So I will go a little to the details. I was trying to run to come to that stage. So parapositronium is the state with the spin 0, angular momentum 0. So spin 0 has it's antisymmetric in spin. So it is antisymmetric in spin. It is symmetric in the configuration space with the angular momentum 0. So antisymmetric, symmetric as a whole, it has to be antisymmetric because these are two fermions. So the charge conjugation is symmetric. And in the same way, one can show that the charge conjugation, so exchanging particle to antiparticle for orthopositronium, which has spin 1, which is symmetric in spin, is odd. So this property is causing that one can decay to the odd number of photons and the other to the even number of photons. And this is the main reason why the time is so different, because this process is much more complicated. There is one more coupling constant, 1 over 140 almost, and the lower space. So this time is about 140 nanoseconds. This is 125 picoseconds. And now inside the body, that parapositronium also decays fastly, but orthopositronium lifetime may be shortened due to 2 reasons. So one is the annihilation of positrons from the orthopositronium with electrons from the surrounding atoms. This is additional process which is increasing the decay rate, so making the lifetime lower. And another process is the conversion of the spin with paramagnetic molecules of oxygen. So if the orthopositronium is interacting with the oxygen molecule, it may exchange the spin with that molecule, becoming parapositronium, and from 140 nanosecond is becoming a 120 picosecond object. So these two processes are decreasing the lifetime inside the body. And this is a process which is occurring when the orthopositronium would decay without any interaction, like in vacuum. So this shows that the measurement of orthopositronium lifetime can give us information, in principle, about the concentration of oxygen, which is the main molecule for the metabolism, and about the size of that free voids here, without the electrons. So the larger are these voids, the longer will be the lifetime, because the lower will be the probability for that interaction. So these are the physics reasons to learn about the intramolecular structure. Now, this is one of the examples that what we can learn from the oxygen concentration. So here you see various tissues. These are these tissue names. But independent of whatever tissue it is, the oxygen concentration here is expressed as a pressure, a partial pressure in that units is in the cancer tissues is lower than in the healthy tissues. And that differences may be converted into the difference of the lifetimes. These differences are very small, so it will be not so easy to learn that. So this is a long-standing development. And to make the first human image, We were trying for a long time to use the scandium. Scandium is decaying to calcium, and then calcium is to the excited state of calcium, and that excited state is de-excited by emission of gamma, again within few picoseconds, in all cases, in 100% of cases. But we are still on the process of getting the permission of the ethical committee for doing that experiments. And therefore, we tried first with gallium, even though it is not the optimal one, because here is only 1% of that cases. But this is the photos from that first images. The patients were shifted here, and the rest I already explained. These are some standard images, and the image of positronium lifetime inside the human brain, showing the differences. So this is the stage we are now. And now we are building a total body PET. So it will be like 2.5 meters with the full sensitivity over the body. We got, after the many, you can imagine, many years of struggle with the ministry, we got €3.5 million to make this PET. Siemens is selling a 1 meter PET for €9 million, and this is not the stage of the development. So it sounds a lot, but it is showing that 2.5 meters for 3 million compared to 1 meter for 9 million is showing that factor 10 effectiveness of that technology, and we will be able to measure all these events. And now, when we change from gallium to scandium, we increase factor of 100 the efficiency. This tomography system is increasing efficiency by factor of 30 with respect to that prototype I have shown you. So now, in some years, we hope to have that images with 3,000 times higher statistics. And then it will be a real images. These are some photos from the construction. And in addition, this tomography system will be like solarium, but it's not working, maybe here. So this is light. So we will use the patient lying on the bed, then making a CT for the anatomic image. And then our PET will come, this will be relatively light. So we have already a design for that. The patient would be able to close and open that, so having a good feeling that can escape anytime. This is the main problem with the claustrophobic feeling. So this will be the whole body imaging with the sandbed-like PET. And now I would like to make some minutes about the physics studies which we are doing. Here the main motivation was to look for the discrete symmetries like CPT, CPT in the leptonic system, positron and electron leptons. By now there are no any sign of violations, neither T or CP. They were only observed in hadrons, in the weak interactions. Here we have no indications. This is quantum electrodynamic. In the quantum electrodynamic, if we would look for the system decaying into like free photons, looking for various operators of that free photons, the limit one can make in principle studies is up to about 10 to minus 9. At that level, the interaction between photons start to play a role via the vacuum polarization. But the present limits of the experimental, or before we started with, were a few times 10 to minus 3, as you see here. So there is like 6 order of magnitudes to research for finding an effect which would be unexplainable by the standard model. Otherwise, nobody expect any violation. So it would be something unexpected. We have started from that operator, spin and 2 momenta, but I will explain you how it works without that operator, so just on that pictorial example. So I will try to explain pictorially what it means to measure or to study the time reversal violation, or CPT. But time reversal is easier to conceptually to explain. So let's think about the decay of orthopositronium into free photons. We have 1, 2, 3. And this has a spin. Now, if we would reverse the time, so we cannot reverse the time, but if we would reverse the time, then that photon would be flying that direction, that photon would be flying that direction, that photon would be flying that direction, and the spin would be turning back, so this will be the spin direction. So now, these two decays, or these two phenomena, are connected by the time reversal symmetry. So the reasoning is like that. If the time reversal symmetry is conserved, then the probability for this should be the same as the probability for that. And now we come to the counting experiment. We have to count various configurations and compare them. So this is what we are doing, and I will show you with that detector. So that detector, we can measure 2 photons, 3 photons. Maybe since we are here, the nuclear physicists, the first question one can ask oneself, how we distinguish between 3 photon and 2 photon if we have in plastics not so good energy resolution, or we can say we have not at all energy resolution. And we base that only on the angles. So let's see for a good event, orthopositronium decaying into 3 photons, and for the main background event, parapositronium and 1 photon scattered. So if you look at that, the momentum conservation tells that 2 smallest angles can never be lower than 180 degrees. There is no chance that all photons goes one direction. So this 2 has to be larger than 180 degrees in a good event. And in the case of parapositronium or direct annihilations and scattering, the 2 slowest angles, so 1 and 2, should be exactly equal to 180 degrees. And these are the experimental data. This is the sum of the smallest angles. So we see here those annihilations into 2, and here are annihilations into 3, and even more, we see here an angular distribution. From the quantum electrodynamics, we know that the most probable configuration is when it is symmetric, 120, 120. So the most probable configurations is to decay into 120, 120, which means 240 degrees. And therefore, there is an enhancement of this here. So this allows us to distinguish, even we can measure in addition the lifetime, but even without the lifetime, we can distinguish between events with orthopositronium and others. So this is experiment, and these are simulations confirming that we understand that system. And for studies of the time reversal violation on CPT, we need to know what is the direction of the spin. But we are doing that without applying any magnetic field. So we use the fact that when positron is emitted in the beta plus decay, it is polarized. Again, very roughly, beta plus decay means neutrino going one direction, neutrino is left-handed, positron going another direction, back to back. This is then right-handed. So if we know the direction of the flight of positron, along that direction, it is polarized, but only along that direction. But we can know the direction because we know the place from where the positron is emitted. And with that phantom, which was previously used as a human phantom, this was in fact done for that studies. So here is a positron flying, and we can reconstruct that position of annihilation. So here you see the reconstructed event. So we know that position of annihilation, we know the position of emission, and along that axis, positron is polarized. Then it goes to the material, and about from 70 degrees of polarization, positrons are becoming like 40% polarized. And these are the final results. So this is now that operator, spin, and 2 highest energetic vectors. This is a cosine, that scalar product cosine, and you see that we got a precision of about 10 to minus 3 really, or 9, 10 to minus 4. Then we changed that to another system, having not cylinder, but a sphere, and having higher statistics. We came to 2 times 10 to minus 4. So now we are at that stage. This is still not published for CPT. So we are now here. And with that modular detector, which will be 10 times more sensitive than that one, we are going to come to about 10 to minus 5. And this is our aim with the detectors. And if we have the total body PET, we hope to come to the level of maybe 10 to minus 6 or even lower. And if I made the last point, so these detectors are also to look for the polarizations degrees of freedom. So if you have a photon which is scattered via Compton scattering, that Compton scattering is at most probable in the plane which is perpendicular to the polarization plane. So these are the Klein-Ishina predictions. This is that angle between the two polarizations and the scattering plane. And for some scattering angles, there is a huge correlations, and the most probable are cases when it is like 90 degree. And we can study here like scatterings of two photons. So then the angle between those two polarizations is giving us the angle between the scattering planes. With that, one can study the quantum entanglement in polarizations of these photons. And these are the predictions of that angle between the polarization planes for entangled state and for not entangled state. I will not go to the details. I will also show you, these are experimental data from our detector. We see it very well with the maxima in the places where expected. And with that, we can also study the discrete symmetries using that polarization degree of freedom by looking for the scattering of the annihilation photon by a Compton effect on the scintillator. So it's similarly like here, we have here spin K1 and K2. We can look here for highest energetic photon, lowest energetic photon, and then the scattered photon, which is, we can order them. So we can have this ordered, which is also important here. So that operator is odd symmetry with P, T, and CP. And we have used that study to determine by now the precision of the CP symmetry violation by 4 times better than it was before. Since I see the chairman standing, I will also only show at the end again. So this is our main achievement as regards the cause-effective PET. So you can go to any place with that. The first image of positronium, and this is what we are going to construct within the next few years and then continue the research. Thank you very much for your attention.
Thanks, Professor Moskal, for this very interesting presentation. 1, 2 hands, 3 hands. We'll leave it at 3 because we are a little bit late.
Thank you, Professor Moskal. When you show this, the discrimination of the orthopositronium in the reconstruction, and then you see that by summing the angles, that you're able, and also by probably making cuts on the time spectrum, you are able to basically fish out the 3 photon events. So what is I mean, you certainly have some 2 photon contributions due to the peak-off events. What is the sensitivity to 3 photon? So basically, what will be the sensitivity to 3 photon reconstruction that you have for the orthopositronium? Or in other words, can I look for a 2 photon decay of the orthopositronium after you subtract the background, like, for example, events that scatter or...
So that image, which is here, maybe I was, sorry, I was not so clear.
You show the triangles. When you show the triangles...
But these were exactly what you well recognize. These were annihilations from the peak-off, so probably from the peak-off to 2 photons. So this spectra and that were not for the annihilations into 3 photons, but to the annihilations into 2 photons. One can do also with 3 photons. In that first case, we did not done that because we have estimated that the efficiency will be 4 times lower. because one need to register one more photon, and they also are absorbed in the body. So we started from that, but one can also do it with 3 photons.
Okay, thank you. And the comment is that since I cannot stay silent concerning your CP violation signal, as you know, we made very strong objections about your claims and about your paper. I cannot comment them here, so I prepare a poster and I invite everybody to
I
look at
am
my poster.
happy to discuss that.
That's
This is one
poster
of
number
the-
10 in the new list. Thank you
Yeah, I
very
am
much.
open for the discussion, and I'm glad that we will have the chance in person.
So I have the microphone. I just had a short question, if I may ask. I was a third person, right?
Yes.
Just a short question. I mean, the body, total body PET scan that you are making. I'm not so familiar with the medical implications, but what is the medical? I mean, normally the doctors inject basically a PET sort of a positron emitting something to part of it and one organ. So why do I need to have this whole body scan?
No.
I mean, what medical use will it have?
Maybe I can show it. Thank you for that question. I will, while jumping, I will start. So the main reason is to have the high sensitivity. So, and this is not injected to the organs. So typically it is injected to the blood. And then it's circulated over the body for about 40 minutes. And then one do imaging now typically at one place. But now the activity is all over the body. And one measure typically with the standard PET, which are about like, so here's on that plot, it's 30 centimeters. So the standard PETs are about half of that. So they measure only about 1% of all the annihilations, or maybe even less. So having total body, one is increasing the sensitivity by about, now in practice, so we can increase with that system by about factor of 20. This Explorer in Davis by a factor of 40. And then you can make 40 times shorter images with the class of patients is increasing or to administer 40 times less pharmaceutical. There is typically a phobia for nuclear. I think it's maybe even better to give more because of this is a joke for the hormesis effect, but the people are very afraid of that. So giving more pharmaceutical is less costly and the people feel more comfortable with that. The children can be scanned, the pregnant woman, and which is not to be neglected. One can see the uptake, this metabolism in all organs at once. And what that means is still not so well known, but it will give some additional information. And having this 40, this is maybe the last advantage I will tell, having that 40 times higher sensitivity, I can make a movie of pharmaceutical, but this is a movie of how the uptake metabolism is changing in a given organ. And the dynamic is different for cancer, different for the healthy tissue, different for various organs. So this is additional information which will allow without the biopsy to more precisely make a guess what kind of illness one is expecting. But there is only one such system except China. China has few because they were ordered, so I think they have few. But in US, there is only one with 2 meters. And that's all for the world. And in 1 meter long are few by now. So this is not something for everybody at present.
Well, congratulations. I have heard from Maria Esther about your research. I'm really very impressed.
Thank you.
Really, congratulations. Now, you have an outer ring, which I presume is for your gamma rays. And then you have this staggered scintillator bars. But it seems to me that you have a lot. Yeah, you just missed it, right? So you have the outer ring. Is that? Oops.
I will show it without that figure.
No.
Okay, sorry.
that I imagine is for your gamma rays, and then you have the staggered, or you can detect, all of them are
All
sensitive.
of them can measure everything.
I see, okay.
And-
And I also noticed you have in fact very few cables, so you have one PMT on each side.
So
The silicon PMT.
this system was completed in 2016. So
Mhm.
it was still with the vacuum tube photomultipliers technology.
Ah,
So, and we had like 200 photomultipliers on one side, 200 on the other side. So it was 400 photomultipliers. But then to really manage that experimentations, we sampled the signals, each signal at 4 thresholds in the leading and falling edge. So roughly 3,500 channels.
I see.
In the
But now you're not using silicon PMTs.
Now we use for that system, which here you see like these are silicon. So you don't see any vacuum tube photomultipliers. It would be impossible. So these are silicon photomultipliers here.
I see. Okay, well, you seem to have, you would increase by having, because there was a problem with count rate. No, you need, you have to increase your efficiency.
So this is, so that problem we overcome with adding more than one layer.
Mhm.
And also I maybe should mention that the efficiency is not that low as from the draft estimations factor of 7 times 7, because in the LISO crystal, only 30% of interactions is photoelectric. So one would need to tell that the registration efficiency for that crystal PET detector is high, but to reconstruct an event with the energy window around the photoelectric effect, then one get only 40% of events. So at the end, with half emitter detector as we have here and 2 layers, we come to the system which is the same sensitive as 20 centimeter standard PET.
I see. Well, when you published your, this is the last thing, it's just a nice comment. When you published your results on the CPT violation, would you give credit to the patient?
So this is a very next step of our research to make a CP, maybe with the CPT violations with the patient. So this studies with the CPT, I'm sorry, I was trying to show too much things and mixed. We're done with the sodium source covered with the porous polymer. So fortunately, we do not need to give credit to this polymer. Otherwise, it's so you may imagine. So I am also a nuclear physicist. To come to the stage to make an image with the patient, this is a very long story, and without the medical here design of all these experiments by Professor Stempin, we will not manage so far.
Okay. Well, thank you again, Professor Moskal. And we have finished our very interesting opening session. Now it's come for time for lunch. So not everyone knows that lunch is part of the symposium. So it's been arranged within the School of Sciences